Hello viewers on YouTube. In this video tutorial, we are going to pay attention to integration by parts. Alright, this is a concept that is used to integrate the product of two functions where the use substitution is not applicable. So what am I saying makes sense? Let's begin by stating the formula for the integration by parts first. It says that the integral of u dv is equal to the product of u and v minus the integral of v du. So what does this formula tell us? It tells us that when you are to integrate two functions where the two functions are multiplying themselves, and you realize that the use substitution cannot be applicable in this case, then you should know that those functions is simply of this form. That is, one of them is an actual function and the other one is a derivative function. Now, the tricky part of this concept is how would you know, how would you tell which is the actual function and which is the derivative function? So in this video, I'm going to show you a clear picture and the best way you can use to identify which of the functions is going to be your u and which of them is going to be your v. So let's begin with an example. Example number 1. Consider this problem. Determine the integral of x sine x dx. So now, you notice that there is no way we can actually apply use substitution here. Before you can apply use substitution, upon setting u to be equal to any of the functions, either u, x or sine x, differentiating u, you must be able to get rid of the other function. If I set u to be equal to sine x, if I differentiate u, alright, and I got the u dx to be equal, the derivative of sine x is simply cosine x. Excellent. Right? Now, there is no way upon solving for the x, I would have the x to be equal to the u divided by cosine x. And don't forget, this will now become u. It will just be as if we are making things more complicated, because by the time we replace the x with this right here, the integral becomes more cumbersome and in fact much more confusing. Alright, so therefore the use substitution cannot be applicable here. Another way you can know, or another logic you can use to tell if the functions cannot be integrated using use substitution is that the first function can be of any index. It can be of one index, most especially the polynomial. It can be of any index. But the argument of the continuous function, either it is sine, natural log, cosine, exponential, and all that, the argument of those continuous functions must be of degree 1. No matter what. It must be of degree 1, or it should be linear. So it's either of the two. So you can't have it as integral of x sine x squared. Alright? Then integration by parts might not be the best one to use, as the use substitution might work in that case. If it is x sine x cubed, the use substitution might still work. You understand? So most especially, the continuous function, its argument will always be of degree 1, or it should be linear. Linear means it should be something like 2x plus 1, 3x, 4x, and all that. Alright? Just like ax. You understand? Where a can be any constant. But it shouldn't be a polynomial. It shouldn't be more than of degree 1. Am I communicating? Excellent. So those are the two different ways which you can use to tell if the use substitution will not work in that case, and instead introduce the integration by parts. Am I communicating? Perfect. Now, the main idea, the main deal is what will be our u, what will be our v. For you to know which of them will be u and which of them will be the v, the derivative. The deal is that at this point, you will end up here. No matter what, you are using the formula, which means if you set any of them to be the v, you will have to integrate it to get v. Alright? Now, what you want to avoid, the deal is that you can actually use any of them. You can say that x is u, or sine x is u, then the v will be the other one. But one thing is what you want to avoid. You want to avoid a continuous repetition of the integration by part process. So that means at this point, for these parts, for this term, we want to make sure that at the end of the day, we're able to integrate it straightforwardly. Not that we still have a product of two functions again that we will need to introduce integration by part again. Am I communicating? So you can, well, it will depend on how you practice. You understand? The more you practice, the more you know the actual one, the best one you can select directly. You understand? But this is what you want to avoid. You want to avoid a continuous repetition of integration by parts. You understand? So it means at this point, we want to be having a straightforward function that we can just integrate directly. So let me show you what I'm saying makes sense. Let's break the board into two equal parts. We don't break, let's split. Perfect. So now, let's consider u to be equal to x and the v to be equal to sine x for the left hand side. And now let's consider the v to be equal to x and the u to be equal to sine x. So let me show you what I'm trying to figure out. It makes sense now. Okay, perfect. Now we need the value of the u. We also need the value of v. Now with this one, we can get the u by differentiating. The u dx is simply 1, and it simply means that the u would be equal to dx. Perfect. Also, we have the v to be equal to sine x. We can actually integrate both sides, okay, with respect to whatever function it is. So integral, this the v you can see it as 1 dv. Integral of 1 with respect to v is simply equal to the integral of sine x with respect to x. Oops, I will do x again. Dx. Excellent. So upon integrating 1 with respect to v, we will have v equal. Now the integral of sine x is simply negative cosine x. Okay, make sure you don't confuse that. Okay, it is the integral of cosine x that is equal to sine x. Don't forget they are actually inverse of one another. Okay, now we have v. We also have u. We also have the v. Likewise the u. Let's plug it right into the formula. So this simply means that the integral of x sine x with respect to x is now equal to the product of u and v. So our u is actually x and v is equal to negative cosine x. And then we have minus x cosine x. Excellent. Then we have minus the integral, v is negative cosine x and the u is simply dx. Excellent. Now we have integral of negative cosine x. So the u is dx. Perfect. Now this makes sense. This is excellent because to now integrate negative cosine x is pretty much straightforward. This is what we need. Am I communicating? Now, by the time we go to the other one, you will now see the difference. You can see, you will now see the difference. So now, what will be the integral of cosine x? Or even before we integrate it, let's simplify this to some part as well. Now, we said the v is x and u is sine x. So we can integrate the v to be now equal to the integral of x dx. And let's differentiate the u with respect to x. The derivative of sine x is simply cosine x. Excellent. Now, integral of 1, the v is simply v. We said it earlier. And integral of x with respect to x is simply x squared over 2. You should know that by now. You should know how to integrate polynomial by now. Okay, I believe that. Now we have, and now we want the u. The u would be equals to cosine x dx. Excellent. Now let's apply the integration by part formula. We have v, we have u, we have du, we have the v. So the formula says that the integral of x sine x would now be equal to uv. U is now sine x, and v is x squared over 2. So we have x squared over 2 sine x. Alright, the minus the integral. We'll also have to multiply v and the u. V is x squared over 2 and the u is simply cosine x dx. Now we have x squared over 2 cosine x dx. Now tell me, how would we integrate this one again? Integration by parts, which is what we want to avoid. Am I communicating? So it means this selection is actually out of the box. So taking the v to be x and u to be sine x would not actually solve the problem. You understand? In fact, you actually did the right thing. It's accepted, but it doesn't solve our problem. You understand? So we need the problem to be solved. So using this first approach is much more better. Am I communicating? So that's what you want to avoid. You understand? That's what you want to avoid. So you are selecting based on what will help you to be able to avoid a continuous repetition of the integration by parts. In fact, who knows that even by the time we integrate this one by part again, we will see end up having another integration by part, and the integration by part will now begin continue showing up. Am I communicating? So that's how you can easily know which of the function you have to use to find or to be your U and to be your V. Are we together? Perfect. So now let's consider more examples so you can actually develop your understanding to full potentials. Alright? So now can get rid of this at this point. So now we can now integrate. So continuing, we have the integral of x sine x dx. So now be equal to negative x cosine x. Then let's bring the minus outside, and when it comes all the way outside the integral symbol, it changes to positive by the time it multiplies this one, and then we just have the integral of cosine x dx. Sorry, or we can actually set that. So this is now equal to negative x cosine x plus, what is the integral of cosine x? That's just sine x, okay? Then we have plus sine x plus c. Don't forget the constant. And this will give us our solution to the integral. And that's it. On to example number 2. Feel free to pause the video and figure this out yourself. Determine the integral of x cosine x with respect to x. Alright? Now, it's obvious that our u would be x and our v would be equal to cosine x. If you are contemplating, you can actually try and undergo all the process we actually went through in the previous example for you to actually be assured that this is the best substitution we can actually make. So now, what exactly is the u dx? That's simply 1. And upon integrating both sides, we have v to be equal. Integral of cosine x is simply sine x, etc. So now, applying the formula, this implies that the integral of x cosine x, according to, with respect to x, according to the integration by part formula, our u is simply x, and our v is simply sine x. Perfect. Then we have minus, according to the formula, the integral of our v is simply sine x, and our du, okay, we are yet to solve for the u, but with what you are seeing, you should know that the u is simply equal to dx, just like 1 times dx. Okay, derivative is not a fraction, but it does work like a fraction. You can cross multiply, you can multiply both sides by dx and all that. Okay, so with respect to dx, because the u is now equal to dx, and final answer would be x sine x. Then integral of sine x is simply negative cosine x. Alright, and if you have minus cosine x dx, okay, we don't need dx anymore. Remember? And final answer will be x sine x plus cosine x plus c. And that's the solution to this example number 2 as well. On to example number 3. I can get rid of this. I should probably be writing the question with a red color and let it be beside the integration by part formula. And we can be using all this line entirely, all the space to solve the problem. So now, on to example number 3, we have to determine the integral of x squared sine x dx. Okay, so our u, now onto white color, is still going to be x squared, and our v will be sine of x. So the u dx at this point is now 2x. By the time we differentiate x squared, we now expect you to know how to differentiate a function. So integrating both sides, integral of the v is simply v, and the integral of sine of x is simply negative cosine of x. Excellent. So now let's apply the formula. This implies that the integral of x squared sine of x with respect to x we now have uv. Our u is x squared, and our v is actually negative cosine of x. Then we have the subtraction sign according to the formula, and the integration of v, which is still negative cosine x, multiplied by the u. Okay, we are here to solve for the u. Okay, what we have right here, you can see that upon isolating the u, we have the u to be equal to 2x dx. So instead of the u, we will have 2x dx here. Perfect. So we have 2x. Okay, it's times actually, and put a dot, 2x dx. Alright, so let's rearrange this. It means this is the same as negative cosine of x. Alright, let the x squared come first. Negative x squared cosine of x. When the minus leave the integral, just like before, it actually changes to positive, and then we have the integral of 2x cosine of x dx. You can actually take the 2 outside anyway. I think that's excellent. So that's negative x squared cosine of x plus 2 integral of x cosine of x dx. Well, this makes sense. There are some situations whereby even with you selecting your u and v to be appropriate, the integration by parts can still repeat itself the second time. But when you solve a problem in relation to integration by part, and you realize that the integration by part process has repeated itself more than twice, well, you can still manage it when it's more than twice. But so far, it's now more than 3 times. Well, I check your problem very well. You might have, maybe you should consider selecting in the other way around. Am I communicating? So, though there are some compound, there are some complex integration by part problem whereby you need to continue integrating until the actual function repeats itself back. You understand? But if you're dealing with a multiple choice question, you can never come across questions that will lead you to actually continue repeating the integration by part process. The maximum it can be should be 2 times. Okay. At maximum, the maximum it can be that which is very rare, should be 3 times. Am I communicating? So please make sure you are fully conscious of that. This means we can actually repeat the integration by part 1 more time. But we did this earlier in the previous example, so we should be able to recollect what the answer is. But for the sake of those who might be quite confused or whose the process might actually get scattered along the way, so it's better we actually simplify everything to this time. So now, before we actually move forward, we need to evaluate this integral. So don't forget, this is where we stop. So let's pay more attention to this integral. And don't forget also the 2 that's multiplying it. All those things you have to make sure you have them at the back of mind. So now we want to pay attention more to the integral of x cosine of x dx. Alright, our u, let it be x. It means the u will be equal to dx. Okay, by the time you integrate the x, you should also, by the time you differentiate x, you should get 1, and then that's it. Now also, our v is equal to cosine x, and the integral, it means v will be equal to integral of cosine x is simply sine of x. So now it means our integration becomes uv, which is x times sine of x, the minus the integral of v du. V is sine of x, and our u is simply dx. Excellent. So it means final answer would be x sine of x. Alright, the integral of sine of x is simply negative cosine of x, and that negative will actually multiply this one and it becomes positive, and we have x sine of x plus cosine of x plus c is not necessary at this point. Okay, you had the constant when we actually finalize the integration. So the integral of this x cosine of x, we got that to be this. So we can actually replace that. Well, let me get rid of this anymore. Later. So bye-bye. So it means our final answer will now be equal to x negative x squared cosine x plus 2. You don't forget it is 2 times. Alright, then we got our integral to be x sine of x plus cosine of x. And you can have plus c, and upon expanding to the least form, we have negative x squared cosine of x plus 2x sine of x, then plus 2 cosine of x plus c. If you have like terms, you can actually try and see if you can add or subtract any terms. But with this, all the terms are different, and that's our final solution. So on to example number 4. So the example number 4, we are to integrate. Okay, I need to get rid of this. The difference is just cosine of x instead of sin x. So it's just cosine of x. So instead of solving it, use it as an exercise. So solve this integral for me and share your solution with me via the comment section below. Now we want to consider some other different functions. So far, we have been considering a polynomial being multiplied by a trigonometric functions. So now, what if it's an exponential function? How do you do that? So let's see. So consider the integral of x, okay, that's too large. Integral of x e to the x dx. Okay, so you might be wondering, are you using integration by part or use substitution? As you can see, you now have a continuous function to multiplying that linear function. So it's obvious, almost obvious that it is integration by part. But for you to actually be 100% assured, the argument of that continuous function must be linear. This is linear, that means we're on the good side. So what will be our u? U is still x, and the v is still equal to e to the power of x. Am I communicating? This makes sense because upon finding the derivative of u, we'll get to 1, which means when we get to this point, it's very rare for us to have two other functions again that are different, that are multiplying themselves, that will need to be the integration by part again. Am I communicating? So if possible, there's a way you can always make the u to be equal to 1 or the u to be equal to the x, and don't hesitate, as that's what will be the best way that will help you. All right, perfect. Or it should just be, it should reduce in its complexity. Understand? X compared to 1, they are different. 1 is quite simpler than x. X can be anything, but 1 we know that is 1. Are we together? Excellent. So now we can proceed forward. So the u dx is simply equals to what? 1, and it means the u will be equal to the x. And upon integrating both sides, v would be equal to e to the power of x. The integral of e to the power of x is still equal to e to the power of x. Is that again? Perfect. So now we can apply the formula. This implies that the integral of x e to the power of x would be equal to uv, our u is x, and v is simply e to the power of x. Then minus the integral of v du, our du is dx, and v is e to the power of x. So final answer would be x e to the power of x minus the integral of e to the power of x is still e to the power of x, and we can have e to the power of x to be factorized outside, and then we have x minus 1 plus c. So that's our solution to this problem. Am I communicating? Perfect. On to example number 6. So this is the 5th one. Come on to the 6th one. So for the 6th one, the difference is that we now have the exponential function to have its arguments to be 2x and not just x with respect to the x. You might be wondering that do you need to use u substitution? No, this is still linear. It's not a trinomial, neither is it a polynomial. So it's linear, as you can see that degree of x is still 1. So just like before, you can see always set your u to be equal to x and the v to be equal to e to the power of 2x. But you have to be sensitive right here while integrating. So what exactly is the u dx? Well, that's simply 1. And finally, we can just write it as the u to be equal to dx. Now, to integrate e to the power of 2x, you have to be careful. Now, integrating the v and the integral of e to the power of 2x with respect to x, the v is simply v. But for this one, basically, you integrate e to the power of 2x, that's the e to the power of 2x. You now divide your result by the derivative of 2x. What exactly is the derivative of 2x? That's just 2 divided. So the answer is e to the power of 2x over 2. Some people might still be confused with what I just said. So it will be better I make it much more in a more open way for you. So basically, let's use t to be equal to 2x. Which means this integral becomes the integral of e to the power of t dx. However, one crucial thing about integral is that when you are integrating, you must be integrating with respect to the variable. Now we have e to the power of t as a function, and we need to integrate with respect to x. So we need to manipulate. So we need the x in terms of the t. However, this equation can help us to do that. What exactly is the t dx? Well, that will simply be 2. Alright, that will simply be 2 because when we differentiate 2x, we will get 2. And it means finally, upon isolating the x, we will get the x to be equal to the t over 2. T over 2. Perfect. So now to integrate it means we can actually replace the x with the t over 2, and then we have the integral of e to the power of t. The t, why is it sometimes my tablet actually misbehave? So the t over 2. Alright, now the 2 can actually leave the integral region, and we have this will equal to 1 over 2 integral of e to the power of t dt. This makes sense. Integral of e to the power of t is e to the power of t, and we have 1 over 2 e to the power of t. But remember, the problem is actually in terms of x. So you must have your solution in terms of x. So let's replace t back with 2x. It means our final answer will be 1 second of e to the power of 2x, which is actually what we got over here. 1 second of e to the power of 2x is the same thing as e to the power of 2x divided by 2. Am I communicating? Perfect. So be very careful when the argument is not just single, when it has a coefficient being attached to it. Perfect. Now we have everything we need. We have the u, we have v, and we have the v. We actually apply the integration formula. So it means that our integral of x e to the power of 2x with respect to the x will now be equal to uv. Our u is x, and our v is simply e to the power of 2x divided by 2. Okay, then minus the integral of v du. Our v is still e to the power of 2x divided by 2, and our u is the same as the x actually. Perfect. So it means simplifying more forward, we have 1 second of x e to the power of 2x. Writing it this way, I think it's much more better. I just make much more sense. And I would like to bring this to outside the integral symbol, and then we have 1 second integral of e to the power of 2x with respect to the x. Well, we integrate e to the power of 2x earlier, and we got that to be e to the power of 2x divided by 2. And this clearly simply means that 1 over 2 x e to the power of 2x minus 1 over 2 multiplied by the integral of e to the power of 2x is simply e to the power of 2x divided by 2. Excellent. So now we could write our final answer. So let's get rid of this one. Therefore, final answer would be 1 over 2 x e to the power of 2x. The minus, when this half multiply its product, we have negative 1 over 4 e to the power of 2x. Well, if you want, you can actually factorize 1 over 2 e to the power of 2x outside. Let's do that actually. So, whatever I'm wondering, you can actually get a clear picture. So 1 over 2 e to the power of 2x in the bracket. When we take these and these outside, left over is just x. So now we can have x, the minus 1 second out of 1/4 is left over with 1 second. This has gone as it's already outside. We have this. Do not forget plus c. And that's our final solution. So by now, I want to believe you should be able to integrate functions using the integration by parts. So that's how you can easily apply your integration by part formula to problems involving integration by part. So in our next video, we will be considering integrating a natural log functions using the integration by parts. So thanks for watching. See you in the next video.